So we are also going to discuss about quantum dots in a little bit, a few other things about quantum dots. So as we discussed that they can be used in lasers and as biological markers. So when we are using them as biological markers, the quantum dots are coated with a material such as a ligand or a functional group. And this functional group is chosen in such a manner that it binds selectively with a particular biological structure, which might be cancer cell or any other kind of cell which we want to and check the location of. So the quantum dots, they bind to these cells and then reveal its presence by absorbing and emitting light. So in quantum dots, if the absorbed wavelength is lambda 1, then the emitted wavelength will be larger as compared to the absorbed wavelength, and it is called Stokes shift. And because of this Stokes shift, it will reveal the location of the cancer cells. And the energy of a particular level will be given by this relation, which is a very simple relation, but and it is quite similar to that what we've got from particle in a box model. Just the difference is that the mass, free electron mass, is replaced by the effective mass of the electron if we are talking about the confinement of electron in this situation. Also, the difference between energy levels. Suppose that we have two energy levels where Nx, Ny, Nz is 1, 1, 1, and for the next level it is 2, 1, 1. Then the difference between the energy levels will be given by the energy for Nx, Ny, Nz is 2, 1, 1, and Nx, Ny, Nz is 1, 1, 1, and you can use this relation and find these energy values. And so we find out that the energy difference between these two energy levels will be given by this relation. Now there will be a difference. In case if it is a cubic material structure, it will be L square, where L will be the length of each side of the cube. While if it is a spherical dot, then we'll have to consider the radius of the sphere. So R here is the radius of the sphere. So let us try to understand what will happen when we move from one situation to the other. Let us say that we are talking about a semiconductor material, which is gallium arsenide. And if it is a cube, we'll take each side to be of length 10 nanometer. And we consider another gallium arsenide quantum dot, which is spherical. And both of them, they have the same volume. So we see that in a cubic quantum dot, the difference between energy levels it is much less as compared to the difference between energy levels in a spherical dot of the same volume. So it means that if it is a spherical quantum dot, it is much easier to get discretization or quantization as compared to a cubic structure. Also, when we consider semiconductor with a metal, you see that if we take a spherical quantum dot of metal and a spherical quantum dot of gallium arsenide, which is a semiconductor, we see that even though they have the same radius, but because they have drastically different effective masses, electron masses, because here it will be effective mass, while in this case it will be free electron mass, because in metals electrons are considered to be free. So we see that the difference in energy will be much lesser in metal as compared to semiconductors. So it means it is much difficult to get discrete energy levels in metals as compared to in semiconductors. So in order to get this much amount of energy difference in metals, we'll have to go to a very small radii of metals of the order of 1 to 2 nanometers. While in case of semiconductors, a radius of 6 nanometers is good enough to get this much amount of energy level difference in the energy band structure.